universe. I'm Ben Dorman. I'm the chair of Friends of the DAO, and I'm glad to see that everything seems to be, apart from the fact that speakers are not quite working yet, up and running. We have dome tours taking place. We had a large number of children in here just before, as you saw, and our planetarium is running. Oh, that's good. Yeah, all right. Okay, I just turned that up next. Okay. It's only about 48. All right. So, are we all ready to get going? Okay, well, I think I want to start now. It's my extreme pleasure to introduce tonight's speaker, Jonathan McDowell, who is speaking to us from Harvard's Smithsonian Center for Astrophysics in Cambridge, Massachusetts. Jonathan and I were undergraduates together at the other Cambridge 40 years ago, and sorry, showing our age. And so I won't say any more on that because he can probably remember some embarrassing stories about me that I don't want him to tell. Jonathan, his day job is as an astrophysicist at the Chandra X-ray Center at Harvard Smithsonian. He studies black holes and quasars and leads the science software algorithms team for the Chandra X-ray Observatory, which is one of NASA's great observatories of the 90s that covered all sorts of wavelength range, of which the most famous one is Space Telescope. And Chandra is the one, apart from Hubble, that is still in operation. Jonathan, ever since way back, has been a hobbyist and a connoisseur of spaceflight. He's been collecting information about spaceflight for about as long as I've known him. And he publishes Jonathan's Space Report on the web, which tells all about the latest launches and the latest things that are happening in orbit. Although this is not quite the distinction it is outside of Victoria, a lot of people have asteroids named after them around here because they discovered it. A few. Jonathan McDowell is the planet 4589, and that's the name of his website, planet4589.org. The number of active satellites in Earth orbit has increased fivefold in the past decade and is expected to increase by at least one further order of magnitude in the next decade. And the advent of large constellations of big satellites in low orbits will transform the night sky, present a challenge to the world of astronomers. So tonight's presentation is about, called A Sky Full of Satellites, and is about the changing orbital population and the impact of megaconstellations on astronomy. So all of those Starlink satellites, which you can see arrayed in the sky sometimes, subject tonight talk. Now I'm going to hand it over. So go ahead.
Hi, and are you going to put up my slides for me?
Calvin. Yeah.
I think they're coming.
Yeah, okay, just checking. And here we go. Fantastic. Thank you. Yeah, so I'm going to talk today about something a little out of the usual run of my astronomical career, the problem that we face from all the satellites overhead interfering with ground-based astronomy. So next slide, please. And so, by the way, thank you very much, Ben, for that intro, and thank you, Friends of DAO, for inviting me. Even before I met Ben, when I was a high school intern at the Royal Greenwich Observatory in 1978 or so, I worked for a guy called Francis Graham Smith, who just had his 100th birthday this past week, and he's still doing okay from what I understand. And he was the Astronomer Royal, and he, as even back then, he realized that satellites were going to be a problem. Back in 1982, when there were only about 300 working satellites, he said the cumulative effect of an increasing number of long-lived satellites represents a very serious hazard to astronomy. And this plot shows how the number of active satellites has increased over the years. And what you'll notice is it's going like straight up right now. That it's increasing drastically just in the past few years. Next slide, please. And so I'm going to talk a little bit, set the scene a bit, and talk a bit generally about how the numbers of satellites have changed over the years. Show you some simulations that I've made of how that's going to affect astronomy. Talk about how we monitor these satellites. Talk about how the satellite companies are trying to make the problem less bad, and how astronomers are responding to the issue. So next slide. And this is just a list of some of my collaborators around the world, just to say that this is all what I'm reporting here is the work of a bunch of people. Thanks. Next slide. So what's the problem? Next slide. And these are some pictures taken in the past few years of satellite streaks on astronomical observations. And you see some of them are just nice little simple bright streaks, but some of them are kind of blobby. And so even automatic software designed to detect them might mistake some of those blobs from a tumbling satellite as galaxies or something like that. So so they're hard to deal with in a fully automated way. And now they're an irritation, but in the near future, we may get to the point where almost every wide field exposure has a bunch of these streaks in them. Next slide. So I'm just going to mention there's also a threat to radio astronomy. Next slide. And I'm just completely going to ignore that because I'm not I haven't done radio astronomy in decades. But here is the optical astronomy problem. So May 2019, we had the first launch of Starlink. And that night, Marco Lambrook took this picture in the Netherlands showing these 60 satellites as bright as some of the brightest stars in the sky. And so we immediately went, oh, we didn't think they were going to be that bright. What happens when there's 100,000 of these like they're talking about? So next slide. And so I organized a bunch of amateur astronomers, actually satellite amateurs, to measure the bunch of the brightness of these satellites once they got up to their operational orbits, 550 kilometers above the Earth, in the summer of 2019. And by the time they got there, they were much fainter, but they were just visible to the naked eye, most of them. But the distribution here I'm showing, and there's some more examples of these trains going overhead when they're very bright just after launch. But typically, once they're in the operational orbit, they were 5th or 6th magnitude, which is just visible to the naked eye from a dark side. But sometimes they're much brighter, up to 3rd magnitude. So next slide. And so yeah, several changes happen once they get to the operational altitude. They also change the way they're pointing. And they made some changes to the design over time that made them a little fainter, but they're still naked eye at least part of the time. And this very first observation, that first day, made it instantly clear that it is technically possible. Like, if you are a supervillain who wants to ruin ground-based astronomy, then it is possible for you to launch. If you're a billionaire supervillain, I should say, you could launch a bright naked eye constellation that would outnumber the visible stars. So Starlink is not going to do that probably, but someone could. And so that will change the night sky for everyone in the world, including non-spacefaring nations that, may not have paid much attention to the satellite stuff, but may care about their cultural connections to the night sky. And we're just seeing the beginning of the next generation Starlinks going up. And some of them are going to be in lower orbits, and they're going to be much bigger. And we don't know for sure yet how bright they're going to be. And some other country could easily license a very bright constellation. And so even if Starlink worked with us to make this not such a bad problem, the global issue is still there for astronomy. Next slide. So I just want to explain to you what a constellation is, because you're astronomers, you think you know what a constellation is, right? It's like Ursa Major and so on, but that's not what I mean. I mean a satellite constellation, which typically consists of a set of shells of satellites where you have, say, 100 satellites or something, all at the same height and all at the same orbital inclination, either all going around the equator, all going around the poles, or all going at some angle to the equator. And you make a ring of them around the Earth, a single orbital plane, and then you, with maybe 10 satellites in, and then you make another 10 satellites in another ring that's like 20 degrees to the east of the first ring, and so on until you've made a whole shell around the Earth. And that's a shell. And then you make another shell at a different height or at a different inclination, and pretty soon you've got a very complex system. So that's what I mean by a constellation. The illustration there is of a 1990s constellation of satellites called Iridium. Next slide. And so I just want to mention that constellations are not new. Even back in the Cold War, there were smaller constellations, and they typically only had 2 or 3 satellites working at a time, but those satellites didn't have any way of removing themselves from orbit. And so there's, for instance, a Soviet system called Strela 1M, which is completely retired now. All the satellites are dead, but all 360 of them are still in orbit around the Earth as space junk. So that's typical of the early ones. And then more recent constellations, the smaller ones, the biggest is one by a San Francisco company called Planet, which has about 200 working satellites orbiting the Earth, and they're little CubeSats, and they have almost 300 still in orbit. So about 100 of them are dead and are going to re-enter at some point. And these modern constellations are either placed in low orbits that are going to re-enter fairly quickly, or they're given engines that can remove them from orbit at a reasonable speed. And so that's sort of the scene until Starlink came on the ground. There's like a bunch of constellations that are about 30, 50, 100 satellites, something like that. But then Starlink's a whole different order. Next slide, please. And so as of today, 4,284 Starlinks had been launched, and most of them are still in orbit. And there's a rival constellation called OneWeb, and 618 of them have now been launched. And so these are vastly bigger constellations than the previous ones, and they've only just started. Next slide. And so when you're going to launch a constellation, if you're in America, you ask the Federal Communications Commission for permission, the FCC. If you're in another country, you also you have to ask the ITU, the International Telecommunications Union. And so we look at the filings and see who says that they're going to be launching satellites. So Amazon is about to join the game. There's a Chinese one with 13,000 satellites planned. This full Starlink constellation is going to be 34,000 satellites. And there's an insane company called eSpace that put in, it's an American company, but it uses a flag of convenience for its filing. It went through Rwanda and asked for approval for 300,000 satellites to be launched over the coming years, which if that's real, then that's just gonna be absolutely appalling for the sky. So overall, just summing this up, there's the potential for almost 500,000 satellites. compared to 1,000 a few years ago. And so it's just a complete change in the level of industrialization of Earth orbit. Next slide. And so how do we study these constellations? This is too small to read, but you get in the filing, you get a table from each company with a list of the parameters of the shells. And if we zoom in on that by going to the next slide. So here's one shell, and it says, all right, for our shell 3 of the second generation Starlinks, they're going to be at 350 kilometers up. They're going to be at 38 degrees to the equator. And they're going to be 48 of these orbital planes, these shells, these rings around the Earth. And each plane is going to have 110 satellites in it. And so if you multiply that together, you get 5,280 satellites in that one layer. And then, you know, the table gives all the other layers. And so that's how you build up to your 34,000 satellites. And that's enough information for us as astronomers to model what these constellations are going to be like in orbit. So if we go to the next slide, just to give you a sense, here's the OneWeb constellation with the dots on the map of the Earth, showing at that point there were only 400 in orbit, showing sort of how they were distributed over the Earth. And this is the picture on the right is a bunch of I think 36 OneWeb satellites all stacked together on top of a rocket stage. So they launch these things many at a time and sort of push them off the rocket stage. Next slide. And the story that's really new, I think, and hasn't got as much attention is that, again, it's not just Starlink and OneWeb anymore. We're getting new entrants to this sector every few months. And so the Chinese are getting in on the act. There's a company called Yinhe Tangtian. eSpace has launched some test satellites, Boeing. And then notably, there's this satellite illustrated in the foreground, which is absolutely enormous, huge phased array antenna for cell phone communications. And this is from a company in Texas called AST Space Mobile. And so this is its Blue Walker 3 test satellite, which is about second magnitude some of the time. And so if they're going to launch a lot of these, that's going to be a real challenge. Next slide. So that's sort of the new feature is these enormous constellations. And I want to give that a little quantitative analysis by showing you the population explosion, the census of Earth orbit, of low Earth orbit particularly. So next slide. And so this plot shows since Sputnik, the number of tracked objects in Earth orbit, which is going up and up and up. And it's now about 25,000 objects tracked. And we think there are actually, and that's sort of most objects above 10 centimeters in size. And we think between 1 and 10 centimeters, there could be as many as 1 million objects that aren't in the catalog because they're too small for the radars to track. And so if you look at all this space junk, you think, well, it's not such a big change. The little cyan tip at the top right there is the Starlink satellites, and they're not dominating. They're significant, but they're not dominating. So maybe it's not such a big deal yet. But that's misleading, and I'm going to show you why. So if we go to the next slide, yeah. So first, I want to talk about the orbital lifetime of satellites. And so I divide low Earth orbit. Low Earth orbit conventionally is anything up to 2,000 kilometers above the Earth. And I'm going to talk about lower LEO and upper LEO and a dividing line of 600 kilometers. And why 600 kilometers? Because to the left of that line, what I'm showing on this graph schematically is this red line shows you pretty much the maximum time you stay in orbit if you're not actively using a rocket engine to keep you in orbit. And that red line says that if you're in the really low orbits, you'll re-enter within a couple of years. As you get up to 500 kilometers, you're going to stay up for maybe 20 years. And above 600 kilometers, you're going to stay up for centuries and maybe millennia. And so in upper Leo, abandoned objects stay up forever. In lower Leo, they re-enter quickly. And that makes those two parts of low Earth orbit very different in their environment. So next slide. And that's just the raw data that I used to make the previous plot, just to show you that I did some homework. Next slide. And so what I looked at is, let's look at upper Leo, that's to say above 600 kilometers, and see what the catalog, the space object catalog looks like. And first, I'm going to look at small things less than 100 kilograms in upper Leo, and this is the junk. And these different colors are different kinds of space junk. And all you really need to know is that the active satellites are sort of like the pink strip that's very thin at the top, and everything else is junk. And so almost all the small objects in upper Leo are debris of one kind or another. And the next slide shows the big things in upper Leo. And these are the ones that are really bad for like the Kessler syndrome, if you've heard for that. And the red and pink are the active satellites, and the brown and purple are dead satellites and dead rocket stations. And so again, the story here is that most of what's up there in upper Leo is old junk and not active satellites. And that it's not changing that much. You see an increase, but it's a kind of steady, slow increase. And why am I showing you that? I'm showing you that because lower Leo looks totally different. And let's look at that now. And so these are the small objects in lower Leo. And this is, I should say, this is for the past 20 years or so. And so you see in the early 2000s, this green color, which is just random space, small space debris, was dominant. And today, you see this pink color, which is active satellites, is the CubeSats. And what this plot is showing you is the CubeSat revolution that starting in about 2015, the small objects in low orbit started to be dominated not by space junk, but by working CubeSats, small satellites. There's a spike in 2019 of debris again, and that's from the Russian anti-satellite test, but that's mostly going away now. But what about the bigger objects in low orbits? Now we look at the next slide. This is the last of these, I promise that, yeah. And here you see something even more dramatic, that there was nothing much going on until a couple years ago. And then there's this enormous cyan-colored spike, which is the starlings. And so things that are big, more than 100 kilograms, and low, below 600 kilometers, are now completely dominated by the 4,000 plus Starlink satellites. And why do I care about stuff that is big and low? Because if it's big and low, it's going to be bright. And so observers are going to see it. And so this plot shows you that although when Elon started launching Starlink, he said, oh, you know, there are thousands of satellites up there already. A few more thousand isn't going to make much difference. Well, I'm sorry, but if you just look at the big and low ones, already with only a small fraction of the Starlink constellation deployed, they're completely dominating the environment. And so that's, if you remember one thing about this talk, then we should remember that. All right, so next slide. So that's the demographics. And so upper Leo, mostly debris, slowly changing. Lower Leo, dominated by active satellites and transformationally changing. I'll also mention that commercial space is now completely dominant over government space. That's a change in the last decade. And Chinese commercial space is starting to become very important as well. And that is going to have implications for us. Next slide. So now I want to move on to how that's going to affect astronomy. And so these are just some illustrations of showing the latitude distributions of these constellations that they all look pretty similar in that they have a dense covering in temperate latitudes between about 51 north and 51 south or so, and then a thinner coverage over the Arctic and Antarctic because, of course, there aren't so many customers there. Next slide. And so if you transform that into asking how many satellites are there as a function of latitude, the different colors here are different shells of a particular constellation, and you sort of add them up, and what you typically get, and this blue line at the top, it is this sort of double humped thing where the most satellites are overhead, kind of near, depending on the orbital inclination of the constellation. And but roughly speaking, if you kind of smooth it out, it's pretty flat until you get up to Arctic latitudes, and then it drops off. But those satellites are not all illuminated. They're not all a problem, right? Because if they're in the shadow of the Earth, you can't see them. They might occult a star you're trying to observe, but mostly they're not going to be a problem. Next slide. Well, ones you worry about are the ones that you're actually going to see illuminated with sunlight. Those are the ones you see going overhead at night. And it turns out the calculation, don't worry, I'm not going to give you math, but the calculation is pretty simple. You're basically asking three questions. Is the satellite above your horizon? Is it night where you are? Is the sun below your horizon? Because if not, then you're an astronomer, so you're in sleep. And is the satellite illuminated by the sun? Is it high enough that even though it's dark where you are, it's light where the satellite is? And so that's as long as you know where the sun is, that's a very simple calculation. Next slide. And so you just plug this in for all the different constellations that are proposed, and I looked at because I don't really believe the East Space constellation is going to happen. I picked the constellations that I think are likely to really happen in the next few years, and that's a total of almost 70,000 satellites that I've been modeling. And so next slide. And so what are the different factors? It's actually really bad if you're in a higher orbit, because if you're in a higher orbit, each satellite is going to be visible by more people. You can see them farther away. And so you can see a larger fraction of the constellation if you're observing. And also, the satellite can see the sun for longer if it's higher above the Earth. And so it's going to be illuminated longer into the night. And it's orbiting more slowly because of Kepler's laws. And so on a CCD image, for example, it's going to sit on one pixel of your CCD for longer, and so you're going to get a brighter trail image. Now, the lower orbits have their own problems. They're going to be brighter overall, and so if you're a naked eye observer, you're going to more likely see them. And also, if your satellite is brighter than 7th magnitude, some experiments in the lab have shown that you don't just get a trail on your CCD, you get all kinds of electronic effects that basically fritz the entire CCD and ruin the whole image. So you really would like to have them fainter than 7th magnitude. All right, next slide. And so I did some simulations, and what am I showing here? I'm showing how many satellites are you going to actually be able to detect in the sky? They're going to be actually illuminated as a function of the time of night. And so this plot shows from left to right, starting at twilight and going through midnight and then going to the dawn at the end of the night. And what you see, and the different colors are different constellations, and I've added them all up to give this black line at the top. And it depends on a number of things. So it depends on what latitude you're at, and I've picked for this simulation 30 degrees south, because that's where a lot of the observatories in Chile are. And it depends on the time of year. And so I've picked the worst time of year because I want to be dramatic. and so this is the summer solstice where they're illuminated late into the night. And what you see is that in this plot, I don't know if you can read the numbers, but there are about 500 illuminated satellites early in the evening, and then less and less of them are illuminated later into the night, and then at midnight it's only about 100. And that's, I should say, that's also for satellites that are more than 30 degrees above the horizon. There are a lot of satellites down near the horizon, but professional astronomers are usually trying to not look near the horizon because it's all murky there. And so this is for things that are above 30 degrees above the horizon. And so the bottom line is that in this simulation, you get 500 at the beginning of the night and 100 even at midnight. And what you can see from the different colored lines is that different constellations dominate at different times of night, depending on their orbits. And so the message there is that it really depends on the details of the constellation, how they're going to affect you. Next slide. And so what are the implications? Okay, 100 satellites at midnight. Do I care? Is that a lot, or is that not very many? So when I do some math and go, well, how many streaks am I going to get on the picture I take? And I'm taking a fairly wide field of view telescope with by professional standards, with a field of view a degree in diameter, and I'm taking a 1 minute exposure. And I get about 1 streak for each such exposure with these numbers. So I would say 100 satellites is a lot, because it means almost every picture you take that's a minute long and a degree wide will have a streak on it. And, you know, plausibly for as the number of satellites increases, or you know, you switch the parameters around, you could get many more than 1 streak in exposure. But that becomes very hard to clean the data. So next slide. And so, but I did admit that I was picking the worst time of the year, the summer solstice. Although I didn't include the satellites near the horizon. If you include the satellites near the horizon, you're getting almost 4,000 at the beginning of the night and 1,000 at midnight. So there's a huge number down near the horizon, 10 times as many as high in the sky. Next slide. And so what this says is that large constellations in low orbit are likely to be naked eye, with hundreds or even thousands of visible satellites early in the night. But they're probably, if they're that low, they're probably not a problem at midnight. They won't be illuminated. So you could change the experience of the night sky for people around the world who do tend to look at the sky in the early part of the night. But it's large constellations at higher altitudes, like 1,000 kilometers, that are going to, you know, are not going to bother the average person looking up in the sky because they're going to be too faint. But they're going to seriously affect professional astronomy, or even serious, you know, amateur imaging. If you have wide field ground-based imaging, you're going to have streaks on almost all your images. Is the threat for these higher altitude constellations. Next slide. That's just to say that other people have done this work and get the same answer. You know, if you believe the eSpace people who want to launch 300,000 satellites, then you're going to have more satellites above the horizon illuminated than the number of visible stars. So that's going to be pretty frightening. And so we really don't want this eSpace constellation to be serious, because you're not going to see the constellations anymore there. You're going to see this moving sky, and that's going to be horrendous. All right, next slide. but you know, I did give you the worst time of the year. What happens if I vary the time of the year and the latitude? Next slide. And so I did a bunch of simulations that show that it's still pretty bad a month after solstice, but next slide. At the winter solstice, this plot on the right shows there's not really a problem at midnight. It's still just as bad in evening and morning twilight, but at midnight, the number of illuminated satellites drops to 0 almost. And so, so you will be able to still do some astronomy in the winter, but you know, not all objects are up in the winter, right? If you're in the southern hemisphere and you want to look at the Magellanic Clouds, those are summer objects, and so you're going to be out of luck. Next slide. And then I just have other plots showing the variation with latitude, and so it's better at the equator. It would be worse at the poles, but there aren't as many satellites, so that saves you. So mainly the problem is at moderate latitudes, which is of course where most astronomers are. And it's going to be particularly bad if you're in the real Cambridge, for example, around 50 degrees north, northern Europe and so on, and southern Canada. Yeah, DAO is not going to be great. And so the latitude problem is an issue. Next slide. So what about space telescopes? Are they in trouble? And it turns out that Hubble is currently about 10 kilometers below the main Starlink constellation. And so these things are passing right in front of Hubble all the time. And, you know, the geometry problem is a little different. The main thing that kind of saves you is that Hubble is a very narrow field telescope. It only sees a tiny part of the sky at once. And so you're less likely to get Starlink. But Sandra Crook published a paper recently showing that even before Starlink, several percent of Hubble exposures were affected by satellite streaks. We think it's going to be at least 20% in the next year or so. So it still is a problem for Hubble. It's just less severe. And if you have a wide field telescope in low orbit, you're going to be in serious trouble. I just want to show you the picture at the bottom right here, which we found, Judy Schmidt found. This is what it looks like when you look at a cluster of galaxies, but a Chinese rocket stage passes right in front of Hubble, only 35 kilometers away, right in the direction it was looking, and you get this enormous big streak. Next slide, please. So I'm going to talk a bit about how I monitor the satellite. So short on time, so I'll go through this quickly. How do you know what these satellites are up to? You get data from the Space Force, and for the main companies, including SpaceX, you get data from them as well to show their altitudes. And so you can see what they're up to. Next slide. And a typical satellite life cycle is like this. It deploys at about maybe 250 or 300 kilometers, raises its orbit, operational orbit about 550 kilometers, and then lowers its orbit and re-enters. But there's some interesting details. It pauses on the way up for something called plane drift, and it pauses on the way down. And so the important thing here that I think is not widely known is that maybe 10 to 15% of the time, the satellite is not at its operational orbit. And so if it's operational for 5 years, at least 6 months of that is in these lower orbits where it's brighter. Next slide. And this is an actual example from a Starlink launch showing 60 satellites going up in 3 groups, and they're delayed due to something called plane drift. and then they operate, and some of them get retired early. You can see them coming down in the middle. And then the red ones on the right are ones that have died in orbit and are slowly coming down due to orbital drag. Next slide. And if I zoom in on the sort of left of that, this is the early months of the launch. You see some of them go up to the operational orbit right away. Some of them wait a month, and some of them wait 2 months before they go up to the final orbit. So the overall process of getting to their final orbit takes over 4 months. And I'm going to skip over that for time. Next slide. And just say I have a web page that shows that this is a little out of date. This is January 30. It shows that how many satellites are launched, how many are still in orbit, how many are still working, how many are in the operational shells. And so I update this web page every few days so that the community can know how much of the constellation has been deployed and how well they're doing. And I do this for all the different constellations. Next slide. And then we have a bunch of astronomers who are monitoring how bright they are. And we'll talk about that in a minute. But I want to talk a little bit about the fact that SpaceX are actually trying to help us. So this is mitigation. The Starlinks are really bright. They have these enormous big solar panels. On the bottom plot, you see them orbiting over the Earth with the panel sticking out from the Earth. The sunlight hits the solar panel coming from the right and reflects it down onto the Earth. Next slide. And so they've tried various things to make it less bright. They tried painting the antennas that had some problems with the electronics. They tried visors shadowing the antennas, but that had its own problems, and they've abandoned those. And so they've made some backing material for the solar cells that makes them less shiny. And they just launched the first couple batches of what they call the Generation 2 satellites that are much bigger. They've launched half-size versions of these that are still, 800 kilograms, almost a ton. Much bigger satellites, but with a whole bunch of new technologies that are meant to make them fainter. So we're going to need to do observations in the next few months to see if that's really worked. Next slide. And this is a plot from SpaceX showing in the purple line how shiny their satellites are as a function of what angle you're looking at them. And then when the blue line is how shiny they think the new ones are going to be, and it's a log scale, so they think at most angles they're going to be 100 times fainter less shiny, I should say, than the old ones. I hope that's true. We'll find out. Next slide. And the other thing they're going to do is they're going to lean over backwards, like in the bottom plot, so that as they approach the terminator, the day-night boundary, they'll get less sunlight hitting the solar panel, but that sunlight will be reflected out into space instead of down to observers on the Earth. And so that's a real cost that they're getting. They need bigger solar panels for the same amount of electricity, and it should really help us in making the satellites less bright. Next slide. So that's nice, but, that's just SpaceX. There are many companies deploying constellations. We can't rely on them all trying to help us. So I want to move on to some final policy comments. The astronomical community is organizing to protect the night sky. We have a working group at the American Astronomical Society. We have had several conferences. We've talked with the UN, the Committee on the Peaceful Uses of Outer Space. We've briefed the State Department and the FCC and so on and so forth. And we now have an International Astronomical Union Center for the Protection of Dark and Quiet Skies at cps.iau.org. It's still getting organized, but this is where we're going to coordinate the astronomical response to this problem. And so we want to work with the satellite companies, those who want to help us. and we want to, but we also want to do public pressure and work with the UN and try and establish that the night sky is part of humanity's heritage and environment, which I hope everyone here would agree. And so, some questions to kind of leave you with. Is the night sky part of the environment? Is it subject to environmental regulations? The Outer Space Treaty regulates space activities and says other countries should give due regard to other countries' interests. Is astronomy a space activity, and do they have to give us due regard? Can we get the UN to say the night sky should be protected? Can we get the US licensing process to make the satellite companies do a brightness assessment? Maybe can we regulate no more than X satellites above brightness Y? And so these are all areas in which the community is trying to organize, pushing on all fronts. Next slide. And so my conclusion is that the mega constellations are going to be a significant change to the orbital environment, but also to the night sky. But the impact on astronomy depends a lot on exactly the orbits that you're using. And so lower orbit satellites are going to be naked eye objects. Maybe you can mitigate that with design changes. And they're illuminated near horizons. So they're going to be a threat to some observations, like maybe searching for near Earth objects, but not most professional astronomical observations. They're going to change the naked eye night sky. But the higher satellites, although they're too faint to be naked eye, they're going to be illuminated all night long in summer. And so they're going to be a real threat to professional astronomy. And wide field telescopes are going to just have to deal with all of these satellite streaks on almost every image, and it's going to be a real problem. And I have a web page there. I've collected some information. I've managed to finish, I hope, in time for questions. And so thank you very much. I hope you find this maybe a little depressing, but hopefully interesting. Ben, back to you.
Great, thank you, Jonathan. Ben, do you want to say something, or shall we get to questions?
About new manned space flight missions. Are these affected by these constellations? And if so, how?
Right. So the question, I think, is how are human spaceflight missions affected by the constellations?
Yeah.
And so like I said, these satellites spend like 10% of their time either orbit raising or orbit lowering. And so even though their operational orbits are not near the space stations, they go through the altitude of the space stations. And so they have to be careful to avoid them. And in fact, the Chinese have gotten really teed off by Starlink satellites passing close to the Chinese space station. And SpaceX says, well, trust us, we won't hit you. And if I'm an astronaut on the Chinese space station and that's the answer I get from SpaceX, I'm not sure that would make me feel really safe. And part of the problem is that these satellites, when they change their orbits, they're not like conventional satellites, which fire a rocket engine and suddenly their orbit's different. They have electric propulsion systems, ion engines, which are continuously changing the orbit. And that means if you are an outside observer trying to predict where the satellite will be tomorrow, you have a much bigger uncertainty than in a normal satellite where you can just use Kepler's laws to say where it's going to be tomorrow, because this thing is changing its orbital elements all the time. And so and so I think that the Chinese are actually right to complain about the way that the satellites are going near their space station. So it is something. Now, the other problem is that if you're trying to launch a satellite, you've got to go through all this stuff, and there are going to be delays due to, oh, we can't launch for the next 2 minutes because there's a satellite going over. You don't want to hit on the way up. And the more satellites you have, the more often you're going to have delays of that kind. Then there are failed satellites that might, slowly decay and come past near object. That's not such a big problem at the moment, but it could be in the future.
Great question. Are there anyone else in the audience here? Yes, sir. So the question is, why is the FCC in the US so willing to rubber stamp all of these satellites?
Sorry, can you say again? Why is the
Why
FCC
is the FCC so willing to approve all of these satellites?
Okay, yeah. Why is it? And it's not just the FCC, but yeah. Why do the regulatory authorities think that this is a great idea? Well, fundamentally because the licensing authorities for space activities often, in many countries, often have the explicit purpose of let's encourage commercial activity in space. That's a government policy. And there are other parts of government that are responsible for let's protect the environment. And so the conversation between those different parts of government is what has to happen. Now, I will say that we have had some success in drawing the FCC's attention to, there could be a problem here. And so when Starlink asked for approval for their next batch of 30,000 satellites, the FCC said, well, why don't you have 7,000 more for now, and we'll see how it goes, and you have to do this and this and this to keep the astronomers happy. And so we did get something. It's maybe not as much as we wanted, but they haven't been completely ignoring us. But in general, I think there is a strong government interest in many countries in promoting space business, and the astronomers have not been fast enough off the mark politically to say, oh, but you also have invested in observatories and you want them to be able to do their job.
Anyone else? Is there anyone? Oh, sorry. Go ahead. Who else other than astronomy has a voice in this regulation?
Right, that's a great question. I mean, we are trying to build a broad coalition of people who care about the night sky. And that includes indigenous groups, for example. It includes, but also, there are implications for the space traffic management, right? All of these objects whizzing around in orbit are kind of a problem there. And there's a research question about when all these satellites retire and re-enter, they burn up in the Earth's atmosphere. And there's so many of them that's actually, for the first time, the input of molten aluminum to the upper atmosphere is going to exceed the amount of aluminum coming in from meteorites. And so is that going to affect upper atmosphere chemistry or the ozone layer and things like that? So there's actually research that needs to be done. And so there's an environmental question to be addressed. And so I think, there are many coalitions that we can make, but who has the money, right? And there are very few players who have the sort of money that the satellite companies have, and so that does put us at a disadvantage.
Anyone online? Okay. In closing, you know, it's past Jonathan's bedtime. You may when there's a big story about space, you may catch him on CNN or some of the other cables. I've seen him being called in as the expert over the last 20, 30 years, multiple times in those when something important in space is happening. Thank you very much for your presentation. I learned an awful lot, and I'm sure everyone else did. And thanks for staying up for us.
Thank you. Have a great evening, everybody, and thanks a lot for inviting me.
Okay.